Good morning, chemistry students. My name is Mr. Adam. This is chemistry. Today is the 20th of May. It is a Wednesday. It is day 5 in our rotation. So we're halfway through the week. We only have 14 days of school left, which is crazy to think about. Only a couple more weeks, but keep plugging along, keep working hard. We have a big unit test coming up to make sure that we all know about molecular shape and smells and molecular formulas and all that kind of stuff. We're going to test on that coming up, not next week, but the week after. And so we'll get through that, and then before you know it, we'll be done with the year. It's kind of crazy to think about, kind of crazy to imagine that we're almost done with our time together, but we're almost there. Keep working hard and keep doing what you're doing. So in today's lesson, I want to talk to you about this thing that we call the electronegativity scale. Okay? The electronegativity scale, in pages 229 through 231 in your books, is talking about, of course, electronegativity again. The desire of certain kinds of atoms to pull in electrons, to bring bonding electrons closer to them. So we talked about electronegativity. We talked about what happens when you have a difference in electronegativity. If one atom is way stronger than the other, it's going to pull all the electrons in towards it, and it's going to become what we call polar. So we talked about what happens when you have a difference in electronegativities. You see polar bonds, you see dipoles, you see polar molecules, right? But now we're going to actually look at what the real electronegativity values are for all the elements. And we're going to be able to take those real values and calculate the difference between two elements in a bond and see if they form a polar bond, or a nonpolar bond, or an ionic bond, right? So we're showing general trends and specific values for all the elements on the periodic table for electronegativity. So let's take a second to look at the periodic table, okay? So you can look at the electronegativity scale or the periodic table. Either, if you're online, it's the first page of the reading, and if you have your book out in front of you, it's page 229. It's also listed in a handout that I don't think's on today's lesson. I think it's on tomorrow's. But let's take a look at the periodic table here. And we look at our scale. Okay? So this is our periodic table without the electronegativity numbers on it. But if you look at your electronegativity scale for a second, where do you find the highest numbers? And where do you find the lowest? If I look at this scale, the highest number I can find is 3.98, almost 4. And that is fluorine, all the way in the top right corner, okay? If I look around fluorine, there's oxygen at 3.44, chlorine at 3.16, bromine is 2.96, sulfur is 2.58. So there are all these high numbers around 3 or higher, or close to 3, in the top left corner. So that tells me that all the high value electronegativity elements are going to be in the top right corner. What kind of elements are those that are in the top right corners? To the left of that, the squiggly line, the staircase, we have all the metals. And to the right, in the top right corner, we have all the nonmetals. So all the nonmetals, for the most part, except hydrogen, which is kind of on the other side, have very high electronegativity values. Okay. So where do we see really low electronegativity values? What kind of elements really don't want electrons that much? That would be the metals, right? The metals on the bottom left side, on the left side of the periodic table, are all going to have really low electronegativity values. And again, think about why that is, right? Do metals really want to gain electrons? Do they really want to pull electrons in? No, they only have a few valence electrons. They're really close to 0, so they'd rather lose electrons to get to 0 than try to gain them, pull them in to get to 8. So, this is our electronegativity general trends, right? If we look at electronegativity trends on the periodic table, we see that it gets lower as you go towards the bottom left, and the lowest electronegativity value on the periodic table, let me make sure I am correct, I am, is francium at 0.7. Okay? So you get lower as you go to the left side, and you get lower as you go down the periodic table. So where are your highest electronegativity values? They're towards the top right corner, right? Fluorine is your highest at about 3.98. So you get higher as you go to the right side, and you get higher as you go up. Your value gets higher as you go up. The one exception, which I've crossed off here, is the noble gases. Now, why would the noble gases not want to pull electrons in? Why would they not attract electrons? Do they want any more electrons? Do they need any more electrons? No, they're very noble and perfect, and they don't need those peasants' electrons, right? They don't need electrons from anybody else, and so they're not going to pull them towards themselves because they're already perfect. They're already noble. They don't need any more. Okay? So noble gases are the exception to that rule, but for everything else, as you go towards the top right corner, you get higher in value, ending with fluorine. As you go to the bottom left corner, you go lower in value until you get to francium. And these trends here are showing you which, if you get higher or lower, if you go in a certain direction. If you go to the right, you get lower. If you go to the left, you get lower. If you go to the right, you get higher. If you go down, you get lower. And if you go up, you get higher. Okay, so this is great. This tells us all the electronegativity values of, all the elements on there. Numbers, elements, awesome. I love all those things. But what do those numbers even mean? What does it mean to have an electronegativity value of 3.98? That doesn't tell me anything. Does that mean you attract 3.98 electrons? Hydrogen only attracts 2.1 electrons? That doesn't really make sense. What does that mean? Kind of nothing. By themselves, electronegativity values don't really tell you anything. So these numbers by themselves in this table, in this scale, don't really tell you a whole lot. You got to put them together. You have to find the difference in electronegativity between two elements. Okay? So one value by itself, not useful. Two values, finding the difference between them, extremely useful. That tells us the properties of that molecule, whether it's going to be polar or nonpolar, and that's going to tell us about its properties, whether or not I can attract it with a staticky balloon or comb or a magnet, right? Whether or not it's going to mix with another molecule or be able to be separated or be able to be smelled. Okay? So if you flip to your next page in your book, 230, you're going to see some examples of what we call diatomic molecules. Remember what a diatomic molecule is, right? Di means two, atomic means atoms, molecule is a molecule. So it's a molecule with two atoms. Okay. We're going to look at one diatomic molecule to start. Excuse me. And that is HCl. Okay. In HCl, you have H, hydrogen, and Cl. Now, using that table that we just were on, we can figure out what each of the electronegativity values are for H and Cl. H is about 2.1, and Cl is about 3.16. Big whoop. Who cares? Why do those values matter? What do those numbers mean? Well, it's about to matter. So now what you can do is you can figure out the difference between these two numbers. So you got to break out your old friend, the calculator. And yes, you can totally use your phones as calculators because I'm not there to stop you, and whatever you need to use, you can use. All right, so I have 3.16 and 2.10. Obviously, you want to subtract the bigger number by the smaller number to give you a positive number. If you do the opposite way, just take the absolute value of it or figure out what it is in negative. So I have 3.16 minus 2.10 for my electronegativity values. My difference is 1.06. Okay, so I'm going to write that down. 2.10 minus 3.16 equals 1.06. So I'm going to circle that. Okay, so 1.06 is the difference between the electronegativity values in this molecule for this particular bond, right? We're looking at the polarity of that bond. Okay, so now we want to figure out what kind of bond is it? Is it nonpolar? Is it polar? Is it ionic? Well, the way we figure that out is we take this number here and we plug it into this electronegativity difference scale, right? It's kind of what we call a continuum. And in that continuum, you see that different differences in electronegativity are going to give you different kinds of bonds. Okay? And because it's a continuum, you can get more and more polar and more ionic the bigger the difference is. But generally, we're going to classify them. If they're in a certain range, then they're going to be that kind of bond, and that's all we'll really say about it. Okay? So, let's look at this. If you're going from 0 to 0.5, this blue region here, we say that that is a nonpolar covalent bond. Basically, those atoms are pulling electrons equally, so there's an equal tug of war for the most part, and so there's not really a difference in polarity. Neither is really attracting the electrons more. Okay? From 0.5 to 2.1, you have a polar covalent bond. That's when one element is significantly stronger than the other one, so it's pulling the electrons towards it, but it's still a covalent bond where they're sharing electrons. It hasn't ripped the electrons completely away, but it is saying that one is going to have many more electrons around it. It's going to have that partial negative charge. It's going to be polar, okay? And then the last one is from 2.1 to 3.3. That would be an ionic bond. So if you have a big enough difference in electronegativity, this usually happens when you have a metal and a non-metal. If you have this huge difference in electronegativity, that's generally going to mean you're in an ionic bond, and one atom is taking all the electrons away for itself, and the other is giving them away or letting them be taken, right? So let's check this out. HCl has a difference of 1.06. Where does it fall on the scale? On the continuum? That'd be right about here, right? So what region would that be in? Between 0.5 and 2.1? That would be polar covalent. So HCl is a polar covalent bond, which we know from last chapter. That Cl is going to take all the electrons for itself, hoard them all on the side, and H isn't really going to be left with a whole lot of electrons. Okay, good. So now let's look at another example, and your book doesn't even go this far. It doesn't go into non-diatomic molecules, but this is fine. We can do this. All right, so now we have this molecule called CS2. It's a lot like CO2, carbon dioxide, except it's got S's instead, okay? And we have two bonds here. Yes, I know we have double bonds. We have two double bonds here, so we can look at the difference between S and C over here, and the difference between C and S over here. Hint, they're the same. So we want to figure out what the difference between S and C is. So we have 2.58 for S and 2.55 for C, okay? So what is going to be the difference between them? And then how could I use that to label the bond? So 2.58 and 2.55, heck kitty. 2.58 minus 2.55, plug that into my calculator, I get 0.03. That's pretty low, okay? So I'm going to take that, subtract that, equals 0.03. So for one of those bonds, the difference in electronegativity of those atoms is 0.03, right? Hi, okay, there's a big cat in front of my whiteboard now. Are you good? Are you done? You going to stay there? You're going to come back across. Okay. So 0.03 is your difference in electronegativity there. Okay, so where does that fall on the continuum? Where does 0.03 fall? Really close to 0, right? So it's very close to 0. That would be in the nonpolar covalent range. So the bond between C and S would be nonpolar covalent. Both of them would be nonpolar covalent, both this one and this one. So let's write that. Let's write nonpolar, NP, no problem. So those would both be nonpolar because the electronegativity difference is so small, because those atoms both want electrons about equally. Neither is really stronger than the other, so neither is pulling electrons more, so it's going to be a nonpolar covalent bond. All right, so in your assignment, which is due tomorrow, you're going to have to talk a little bit about the electronegativity scale, what it means, what the general trends are. You're going to talk about calculating electronegativity difference. And then for the last 3 questions, you're actually going to calculate that electronegativity difference. So you're going to do what we just did in some examples. You're going to take your 2 elements, find their values, find the difference between them, and then rank them on this continuum, or sort them on this continuum. Okay? So that's your goal for tomorrow. Think you all should be fine. If you have any questions, let me know. Send me an email. Hit me up, and we'll talk. Guys, we're real close to the end. Keep working hard. We'll get through this together, and next year we'll be good to go. I don't have anything else to say. Nothing exciting or special. All right, I will see you all tomorrow. Thank you very much. Let's get a 1, 2, 3. Clap on me. Thanks, guys.